Okay, that's that. So my name is Bhawani Venkataraman, as Kathy suggested for the recording, and I really appreciate. Thank you so much for that the invitation to speak here today. So as Kathy pointed out, the theme of water is something that is very near and dear to my own heart. It is certainly a theme that I have been using for a while now to connect, to help students see the significance of chemistry that they're learning in the classrooms to larger issues of social challenges that we face. And in particular, in my courses, I tend to focus on access to safe drinking water for reasons that I hope I will clarify over the course of this talk this morning. But clearly, water is has multiple ways one can explore the context of water. For me as a chemist, water, I believe, is a very powerful way for students to help make the connections between the molecular scale, the macro scale, and the world they live in, and the social challenges that we're facing today. In many ways, water can be considered to be a relatively simple molecule, i.e. 2 hydrogens and 1 oxygen. But in fact, that chemical formula is a bit deceptive, because even at a chemical level, water is an extremely complicated system. And clearly water in a social context is fraught with all kinds of complexities and that we need to grapple with. As I saw in the text chat early this morning, somebody put in a quote that is often used by Native peoples around water being life. And so clearly we require water. But what I'd like to talk about today, life requires water, is an essential ingredient for life. But what I would like to talk about today more is sort of this context of connecting water and public health through access to safe drinking water. And again, that's something that today we're sort of clearly aware the implications when public health is being challenged, as we are currently now in a pandemic, and the implications for that on multiple levels. And so using public health as a way to think about water and safe drinking water was something that I thought could help students connect their prior thinking about chemistry to the social challenges around access to safe drinking water. But before I talk about, why I believe that water is an effective and integrative theme to connect science and society, I'd like to talk a little bit about the institution where I'm at. And one of the main reasons I like to do that is because in many ways, how I came to think about my teaching of chemistry is a direct result, consequence of where I'm currently located. So I'm at Eugene Lang College of Liberal Arts, which is the liberal arts division of the New School in New York City. And the institution as a whole, the New School as a whole, prides itself as embracing progressive social justice approaches in its educational mission. And that's certainly something that at Eugene Lang College too, we pay serious attention to. We want our students to grapple with these real world problems, these complicated social challenges that we face. But we also want them to think about how, the importance of liberal arts education in thinking through these problems. In other words, the idea that no single discipline is going to be able to allow you to integrate in its full complexity these social challenges, and also to be able to, while you might have a major, while you might delve deep into a particular discipline, the importance of cross-disciplinary connections, the importance of interdisciplinarity in looking at these large global challenges is something we also wanted our students to grapple with. And the other element that's also central to our education at the New School and at Lang is sort of framing our thinking, our education around principles of social justice and equity. That is, we want students to not only appreciate the interdisciplinarity of these problems that we want to interrogate, but also how can we come up with ways to address them that really embrace and center issues of social justice and equity. And so, I came to the New School over 17 years ago now, and my own education was arguably just diametrically opposite to all that I've just talked about, the importance of interdisciplinarity in thinking about these problems. I did my undergraduate education in India, and my bachelor's degree in chemistry was really just focusing on the physical sciences and mathematics. All I did was physics, chemistry, and mathematics. And then I came to the United States for graduate school and further narrowed in chemistry, and in my case, physical chemistry. And so for me, in many ways, to find myself at a place at Eugene Lang College was quite different than my own educational training. But it really, therefore, made me think about very critically, what does it mean to teach chemistry in a liberal arts context? The majority of the students who are in my classroom are not going to go down the path that I did. And arguably, that's probably the case for many students in an introductory level general chemistry course. They're there for a variety of different reasons. A subset of them will become chem majors, but that's not true for a majority of them. And so what I started to think about is, okay, given my institution's embracement of interdisciplinarity, given my institution's thinking about framing our teaching and our learning through issues of social justice and equity, how can I see the role of chemistry in that approach? How can I make students understand the relevance of chemistry to the liberal arts education? And as I started to dig into the chemical education literature, I also began to recognize that for a number of our students in chemistry, they often don't see the significance of chemistry. What is it why are they learning, these seemingly abstract and seemingly esoteric concepts? Because it's at a scale that is so infinitesimally small. It's beyond what we can even, think, we can imagine about. So for them, it's like, why does this matter to my day-to-day existence, to what I'm interested in, to what I'm passionate about? It's hard for them to make those connections. And so what I wanted to think about is, how can I come up with ways in which I can center that, make it evident to these students why chemistry might be important for them to think about issues that they're motivated by, that they're engaged with. How can chemical research inform solutions and policies to some of these challenges? How can chemistry be an additional lens for this interdisciplinary thinking? And how can chemistry, thinking about a chemical approach, also help advance or sort of strengthen this commitment to issues of social justice and equity? And so I began again to explore, ways in which the education literature has sort of indicated ways to make chemistry relevant to students. And I came across this whole body of literature on context-based learning. And this text here is from a series of articles that was published a while back in 2006 in an issue that was focused on context-based learning. And as you can see from the various quotes here, the point of using a context, particularly one that might engage a student, is to motivate students to want to understand deeper the fundamental principles that can help them understand the context. So in the case of chemistry, it should be a context where it's understanding the chemical principles of this context is central to interrogating the context. That is, it shouldn't be an add-on or seem superfluous, but in fact, integral to understanding the context. And so in this way, students can begin to learn these chemical principles, but also begin to see why they're learning these chemical principles to understand the context. They can begin to learn the chemical language that's necessary, that we would like them to come away with, so they can have fluency in conversing with other chemists or with other people, but also to see how they can apply this chemical knowledge. And then finally, as we all know, learning also happens when you can sort of build on your prior knowledge. We all come into a space with prior thinking, with prior understanding, and if we can see how to connect what we're learning to something that we're familiar with, or that we probably have questions about, or we want to advance our thinking on, it also therefore sort of helps make the learning more significant and relevant to the individual. And so I said, okay, so context-based learning might be a way for me to think about how to make chemistry relevant to these students, and drawing from literature as to how I might design courses using this pedagogical approach. And then more recently, again, many of you may be aware of the importance of systems level thinking in our classes. And so again, this is some quotes taken from an article that appeared in Journal of Chemical Education in 2019, And this, again, this particular issue of Journal JChem Ed was focused on systems thinking and chemistry. And as this text again one shows, we, again, as educators, we need to begin to pay attention to the fact that our students are learning in our classrooms, but again, to help empower them to take this learning into the broader world that they live in, the larger systems we live in, into the systems of society that, if you'd like, that we live in. And again, the role of chemistry in that. So as this text here quotes, for a chemistry major, it's certainly true that chemistry as a discipline has helped advance a lot of technologies, a lot of the materials that we rely on. But it's also true that because we haven't paid attention to what happens to these materials once they come out of the laboratory into the environment, the implications of these on Earth systems, the impact they've had on ecosystems, on human health, and so on. So if we can begin to frame our thinking of chemistry for our majors so that they are thinking more, they're thinking about what they're learning in the classroom, the experiments they might be doing, the research they might be doing, and the implications of that research, so that they can think about it, they can use the same chemical principles, but they can be more intentional about the implications of the chemical research in the larger society, for example, around resource management or recycling or minimizing the impacts of exposure to pollutants to ecosystems and to humans. And so the idea of systems thinking is also something I think that's going to be critical as we educate this next generation of students. And this is the case not only for chemistry majors, but all our students in our science classes. Ultimately, students that are in our classrooms are going to become the next generation of voters and professionals. And again, how can they use evidence-based thinking in informing their own practices, but also, for example, who they might want to vote for, which political representative is actually drawing from the sciences to inform their policies, to inform their solutions, again, connecting the science and society and so on. So, so this sort of led me to bringing together context-based learning, bringing together systems thinking. I began to sort of say, okay, so what are ways in which I can teach students chemistry that, again, uses a context that they have a lot of familiarity with. And clearly water is something that we all have a relationship to. Many students are familiar with, and we all know that water is essential for life. And we also know for humans, we can't survive more than a few days without consuming water. And so they come into the classroom with that prior knowledge, with that prior understanding. But what I want them to think about is it's certainly true that water is essential for life. And we can explore from a chemical perspective, what is it about H2O that dictates the properties of water that make it essential for life? But how do I bring it into the social context? And that's what made me to think about access to safe drinking water. So when communities have access to safe drinking water, it really undergirds, if you like, the community's health. It makes, it protects public health. It allows young kids to be able to go to school because they're not missing out on days because they're sick. It allows young girls to not be spending inordinate amounts of time to collect water so they can spend time in school. It gives women opportunities, again, takes away the stress of them having to collect the water. It therefore is going to allow communities to be most socially and economic productive in terms of how their time is being used. And so access to safe drinking water is sort of a fundamental requirement, if you like, or need for communities to be healthy, and healthy in multiple ways, from a public health standpoint point of view, but also socially, economically, and so on. And so sort of trying to understand what is it about water that makes it essential for life, but what is it about safe drinking water that from a public health standpoint, we need to pay attention to? What is safe drinking water? And what is, how can we sort of come to sort of recognize that there is this global challenge on access to safe drinking water? For me, and I would assume for the vast majority of the people who are in this symposium today, we don't think about this. We go to our taps, we open the tap, the water comes out, we drink it. In a country like the United States, the vast majority of the people here, we have 24/7 access to safe drinking water. And we're not cognizant, we're not aware of what is happening behind the scenes to take the water from source to tap so that I can go to the tap and consume it and not think about that I'm going to get sick by consuming it. This is unfortunately not the case for a significant fraction of the people across the globe. Some statistics suggest that 1 in 4 people across the globe struggle with access to safe drinking water. And these statistics are rather grim, rather dire. And these are, again, the kinds of prior knowledge that students are coming into the classroom with, because they sort of have heard of these challenges that many communities across the globe face in accessing safe drinking water. The staggering number of hours, for example, that women in sub-Saharan Africa are spending to collect water every day. I mean, just imagine that time could be used in other ways if these communities had access to water. And so, there was sort of recognizing the importance of access to safe drinking water to the health of communities is why in 2010, the member states of the United Nations voted to recognize access to safe drinking water and sanitation as a fundamental human right. This then led to things like the Millennium Development Goals to encourage countries to invest in the resources to meet these goals, so that poverty reduction was sort of central to these goals, and to help provide funding sources for communities to meet these goals. And over the time in 2015, the MDGs and that are the Sustainable Development Goals. So we're now sort of in the period where countries are striving to achieve these SDGs. And as you can see, there are 17 SDGs as mentioned on the slide here. And you can see that access to clean water and sanitation, which in the Millennium Development Goals was part of environmental sustainability, has now been pulled as its own goal. And the other thing that you can also begin to think about is sort of the connections between realizing the goal 6, clean water and sanitation, and many other goals that the United Nations states have committed to realizing for their citizens and their nations. If you have access to safe drinking water and sanitation, as it's going to help address gender equality issues, it's going to help improve educational outcomes, it's going to protect health, it's going to help protect or reduce poverty. So the interconnections between these SDGs are also critical for students to explore. But in the context of water, how water in many ways is going to be sort of the sort of essential need, if you'd like, from a societal perspective, to sort of realize a lot of the other SDGs that global nations are trying to achieve. And so again, this text here is from the United Nations website, and basically summarizing what I just said about the importance of SDG 6 for poverty reduction, for public health, for peace and prosperity of communities. And so you can sort of begin to see how access to safe drinking water might be a way to help connect the science of water to the social dimensions around safe drinking water. And what I also want the students to think about is that this goal SDG 6 is not just something for people in other nations to be thinking about. A lot of the statistics that I showed you in a couple of slides earlier on, it's certainly true that a significant fraction of the population of the people who are struggling with access to safe drinking water are what are residing in what we call global South nations, and a result of that, of historic colonialism and so on, leading to these kinds of huge global disparities. But even here in the United States, as I said, even though while I might have the luxury of opening up my tap and drinking the water out of it and not thinking about its safety because I'm going to take it for granted, that is not the case for large fractions of the population that live in the United States. Data suggests that over 8 million people have for decades struggled with access to safe drinking water in the United States. 8 million people is about the population of New York City. And a lot of this is a result, again, of historic inequities. For example, communities living on native lands are not provided access to municipal piping systems. So they don't have the pipes that are coming into the communities that is connecting them to a water treatment facility to help deliver the safe drinking water. This is also the case with a lot of low socioeconomic communities that have been left out of the infrastructure decades ago to connect them to municipal water systems. So that's a significant number of people that in the United States are struggling with access to safe drinking water. But it's also something that I think that is becoming a growing threat as we have sort of invested in the early 1900s in the infrastructure to deliver safe drinking water, and then sort of assumed we have solved the problem and are not paying attention to the fact that it requires constant maintenance, constant upgrade, constant upkeeping as the science advances and tells us that we need to be doing more to maintain this quality of safe drinking water. There are communities in the United States that routinely receive boil alerts, which mean that the drinking water systems have been compromised. There's exposure to some pathogens in the drinking water systems, that they have to boil the water before they drink it. We have heard tragically of a community in Flint, Michigan that struggled for over a year of trying to raise awareness to their state and city representatives that the drinking water quality was clearly being impacted by a dramatic shift in how the city decided to maintain its drinking water system that led to exposures in the community to lead in their drinking water. And in spite of the community demanding attention to this problem, they were not paid attention to. And the reports that have come out of this really show that a lot of this was a result of systemic racism in how the Flint community was basically not paid attention to in addressing this lead contamination of drinking water. And tragically, lead contamination is a result of historic reliance on lead service lines in drinking water systems. And to maintain the chemistry of the water to minimize lead contamination requires a lot of expertise and understanding of the chemistry of water. And this, in fact, many other communities across the United States has been grappling with lead contamination in drinking water. Another growing concern in the United States and globally is the presence of perfluorinated alkyl substances, PFAS, in drinking water. Again, a result of reliance on chemicals that were introduced in the early 30s, and which were deemed to have really amazing properties, which led to compounds like Teflon, which led to stain-resistant fabric, which led to firefighting foams, arguably things that we feel we need. But again, the chemistry of these compounds were not considered when they were being introduced into our use. And we're now finding them present in our drinking water. In fact, when DuPont first produced these compounds in the 1930s, their slogan was "Better things for better living through chemistry." And maybe that was the case back then, but since then we've realized that we need to begin to pay attention to the chemistry of these systems that are being released in the environment, because it's ending up in our drinking water and it's creating, ecosystem and human health impacts as a result. And, we can sort of keep going on in the ways in which we're sort of realizing that drinking water, safe drinking water, is something which is threatened, which is not something we can take for granted, because the ease with which water can get contaminated. So, and then I'll sort of end with this and then move on into my own class, is sort of again showing the disparities in the United States around who has access to safe drinking water and who doesn't. This slide comes out of a recent study which tried to map out the extent to which utilities are able to meet the drinking water standards as dictated under the Safe Drinking Water Act in the United States. And you can begin to see the utilities that have the most violations in meeting drinking water standards tend to be communities which are rural and low income. And again, it's a result of the expenses that have to be realized in maintaining these capital-intensive infrastructure systems, the expertise that's needed, the compliance to drinking water standards, all add up to actually being a fairly complicated, resource-intensive process. And again, communities that don't have the revenue base, if you'd like, to support these expenses, these are the ones who are struggling in delivering safe drinking water to their communities. So what I hope I've been able to show so far is that there's multiple ways in which one can connect, obviously, drinking water to social challenges. But what I want to now say is, what does it have to do with the chemistry of water? And so this is what I've been trying to think about, how to connect the deep learning of chemistry and the social challenge around access to safe drinking water. And so in looking at this slide here, we're all familiar with these properties of water that have made it essential for life. The high boiling point of water, the fact that water has such a high boiling point is why it's liquid under Earth's surface-like conditions. And because it's a liquid under Earth-like conditions, it allows key compounds to dissolve in it to allow for the basic chemical processes that finally led to life being established here on Earth. The fact that the solid is less dense than the liquid, i.e. ice floats in water, is also something that's beneficial for life. I know every time over a winter season, the lakes don't freeze from the bottom up, they freeze from the top, and so organisms can continue thriving. It's the fact that water is present on all phases of Earth allows the hydrological cycle. And the one that I'm really going to pay close attention to for the rest of the talk is this universal solvent property. Again, we really talk about water as being this amazing liquid, which it absolutely is, right? Because we are here, we're all present on Earth because liquid water is present on this planet. The conditions of Earth allow liquid water to be present. It has this amazing property of being able to dissolve a wide range of compounds, covalent and ionic. And it's because of that, once compounds dissolve in a liquid medium, they can interact, they can react, and they can sort of set the stage for the biochemistry of life. But paradoxically, the same property of water that makes it the universal solvent also means that water is going to dissolve compounds regardless of whether it's beneficial to life or potentially harmful for life. And so I guess the paradox that I want my students to think about is that what is it about the H2O molecule that dictates the properties that make it essential for life? But what is it also about the H2O molecule that dictates these properties and make it easy to get contaminated and therefore potentially a threat to life? And if we sort of understand that deep chemistry, how can we use that chemical perspective to then inform how we manage water, how we protect water, how we regulate water, how we treat the water, so that at the end of the day, communities can have access to safe drinking water in ways that are sustainable and equitable. And so the way I've done this is sort of in a few ways, but I'm going to talk primarily about this introductory level chemistry course that I've developed. This would be equivalent to, let's say, a first semester general chemistry course. And so in this class, I want them to learn the kinds of concepts that a student might in a first semester general chemistry class. But I also want them to think about why are these concepts relevant to their interests, to their day-to-day existence, and to the social challenges that they might be interested in engaging with. So the class itself is divided into 3 units. Access to safe drinking water. We then look at our reliance on fossil fuels, and then we end the semester looking at materials and polymers. But for the purpose of this talk right now, I'm going to focus on access to safe drinking water. And as the slide here shows, I want them to be able to see the connections between the chemistry they're learning and to the social challenges, so that they can make this connection between science and society. So as the learning outcomes indicate, yes, I want them to learn chemical principles, but I want them to see the significance of these chemical principles to these larger social challenges that we're facing around in this particular case, access to safe drinking water. And there are also some skills that I want them to develop. There's a project that they do that I'll talk about, where they can begin to think about using the evidence-based arguments, drawing from the research literature to understand issues around access to safe drinking water. So for this water unit then, what I've shown on this slide here is a way of sort of organized or framed this unit. On the left-hand side, you see a series of framing questions that introduce the class to. So we begin the semester and I have the students read a series of sort of news articles that look at issues around access to safe drinking water, both domestically in the United States as well as globally, to help sort of provide the frame and the context and to introduce them very quickly to the social challenges around access to safe drinking water. And then we begin to say, okay, so in order to understand why is it so challenging for communities across the globe to have safe drinking water, we're going to explore from a chemical lens. What is it about this water molecule that results in it being so easily contaminated? And how can this chemical lens then allow us to think about how we might want to manage and deliver safe drinking water to communities across scales? And so, like I said, on the left-hand side, you can begin to see how the questions sort of begin at the more molecular scale. And over the course of this unit, we're going to go from molecular to macro to social, again, sort of cutting across scales, that systems level thinking being sort of embedded in how we're going to look at these issues over this unit. And on the right-hand side, you can see a list of the chemical concepts that we're going to introduce. And for anybody teaching chemistry, these are ones that you would immediately recognize as ones that are taught in a first semester chemistry course. So I want them to really understand water at this deep molecular level. I want them to understand, what is it about the electronic structure of hydrogen and the electronic structure of oxygen, that when they come together in the ratio of 2:1, 2 hydrogens to 1 oxygen, that is then going to dictate the properties of the water molecules. So we look at, periodic trends and periodic properties, atomic radii and electronegativity, all the things that you would look at in a general chemistry class, but again, framing it as to what makes hydrogen hydrogen, what makes oxygen oxygen in terms of its electronic structure. Why is it that when these three atoms come together, it dictates the nature of the chemical bonds between the hydrogen and the oxygen atom? Why does that dictate its molecular geometry, that is water being a bent molecule as opposed to linear? How is it the bonding between these three atoms end up with oxygen having the non-bonding electron pairs? And we're not just looking at the water molecule alone, we're looking at a range of molecules for them to compare and contrast. We might be looking at ammonia or methane or amino acids. A whole range of compounds that you might typically look at this level of class, but using water as a way to sort of begin to understand what is making 2 hydrogens and 1 oxygen distinctive in terms of their the molecular structure and properties. And then introducing electronegativity, the oxygen atom, given its position in the periodic table, being a very electronegative element, which is going to dictate the fact that the OH bonds are highly polar, the bent structure making the water molecule a very polar molecule, the non-bonding electron pairs along with the polarity of the molecule, then dictating how water molecules can interact with each other through very strong intermolecular interactions, the polar interactions, the hydrogen bonding interactions, how this network of hydrogen bonding interactions is why water has such a high boiling point. And so the fact that water is a liquid on Earth's surface is a direct consequence of the molecular nature of water. And then leading into solubility, looking at intermolecular interactions, the role of solids dissolving in solvents, again, sort of focusing on the high polarity of water that allows it to dissolve this wide range of compounds, from covalent to ionic. And it can even, because of its high polarity, dissolve non-polar compounds, albeit to much lower extents. But the fact that you have dissolved oxygen present is because of the induced dipole interaction between water and the oxygen molecule that allows oxygen to dissolve in water, which is why aquatic organisms can have aerobic respiration. But for this very same reasons that water is this amazing universal solvent, we can then begin to see, okay, it's going to dissolve compounds regardless of their toxicity to ecosystems, to human health, and therein lies the challenge. The same property that life relies on, i.e. universal solvent, is going to make it susceptible to contamination, because any natural body of water that's out there is going to be exposed to things that are in the air and the soil, to effluents from industry. It's going to end up in the water. And if it ends up in water at sufficiently high concentrations that the toxicity is of concern, therein lies the challenge. And in addition, because water is life, life requires water, any body of water is going to have life thriving in it, some of which will be microorganisms. And again, the vast majority of microorganisms are going to be are not going to be harmful, but you could have a subset of them with a pathogenic. And so the point the students come away with is that any natural body of water will have chemicals, will have microorganisms present. Doesn't mean they're unsafe, but because water is this universal solvent, we need to begin to pay attention to what is in the water before we consume it, before we treat it, before we manage it. So in terms of content-based assessment, I have homework assignments, I have ways to assess the conceptual understanding of these concepts, but really also what I'm interested in, and for the purpose of this talk, to talk about how I help students connect this deep molecular understanding of chemistry to this challenge on access to safe drinking water. And I've sort of developed this two-part project where in part one, they're beginning to connect the molecular nature of water to the policy sphere, particularly when it comes to safe drinking water management in the United States. And in part two, I actually want them to think about, well, there's a whole range in which we can think about drinking water treatments. Not every community might have the resources available to have these large infrastructure intensive approaches. Are there other ways in which chemistry can think? We can use chemical principles to look at more appropriate point of use community-based treatments that might help communities have access to safe drinking water. And then I finally end with a reflection so students can sort of talk about what it is they've learned in this project. So just to very quickly go over part one, it's not so much a paper as much as I sort of have identified questions that I want the students to respond to. And in responding to these questions, they're required to draw from all that we've talked about in the water unit, but also to draw from external resources, that some of which I provide to them and others they are supposed to find on their own. And these are resources which are accessible to them, but it's going to introduce them to new ideas that we haven't directly talked about in class, but what I'm hoping that they can begin to see how the chemistry they've learned in the class will help them understand the applications of the chemistry. And so again, we begin at the molecular level. I want them to summarize their understanding about the nature of the molecule that makes it essential for life, as well as potentially easily contaminated. What does safe mean? How can we measure safe? Who measures safe? Who dictates safe drinking water? This is coming more into the policy realm, where in the United States, we might be looking at the Safe Drinking Water Act, regulated under the EPA, for them to understand what that means. How did it come to be instituted in the United States? What is the goal of the Safe Drinking Water Act? How does the EPA dictate or determine when the water is safe? So introducing them to terms, to concepts that will allow them to then, by the end of this unit, begin to understand what does it take for water to go from source to tap in a nation like the United States, so that the water, when they open up their taps, we can sort of that safe drinking water is the goal of the Safe Drinking Water Act to be delivered to homes. And then finally, to also bring it on a more personal level, to also make them pay attention to the information that they can begin to access to assess the quality of the water that's being delivered to their homes. So the Safe Drinking Water Act requires every public utility to publish annually a report that describes the water quality that the community is receiving. And so students I ask them to go and look at their local community drinking water quality report and begin to say, okay, what is happening in their own town? How does the water go from source to tap? And are they comfortable with what their community is doing in delivering drinking water to their towns, to their homes? So like I said, in part one, it's very US centric. And like I said, it really focused on looking at from molecular to policy dimensions in the United States. In part two, I want them, like I said, to think about sort of this global challenge around access to safe drinking water, and to think about there's multiple ways we need to think about this challenge. There's no one solution that's going to be appropriate or accessible to communities across the globe. But again, how can we use science? How can we use chemistry to inform solutions which are appropriate across scales, that also are respectful of local cultures, of local economies, of local practices, so that at the end goal is you would ideally like everybody across the globe to benefit from access to safe drinking water. So in part two, I have them look at a more community-based approach to drinking water treatment. And once again, I've defined questions that they're responding to. I provide them this website from an amazing organization called Center for Affordable Water and Sanitation Technology, which is basically an NGO that is a huge repository of different approaches that communities can consider adopting to treat the water in their town, in their communities. Like I said, these are particularly designed for more rural communities rather than urban locations. And for many of these communities, one of the primary contaminant of concern is really microbial contamination, often a result of sanitation practices. And this also raises an interesting question for students to grapple with. Exposure to pathogens, we might almost feel the impact immediately, whereas chemical contamination is something which often is a case of long-term exposure when people start feeling the impacts of. So for many communities across the globe, it is this immediate impact of exposure to pathogens, which is causing severe, like I said, the public health impacts, the socioeconomic impacts. And so there need to be ways in which that immediate concern can be addressed. And there are multiple ways in which this can be addressed. And so students research different technologies, different approaches to doing that, and come up with ways to sort of understand what are the benefits of these treatments, but also what might be some of the things that are not being addressed for these treatments. So to do a sort of a pro and con analysis. But I also want them to look at some of the studies which have demonstrated the efficacy of these treatments in these communities. So again, an element of introductory to research methods in coming up with whether or not they would propose a particular treatment that they've chosen to research to a community, and why might they do so. And then, like I said, I end with have students reflect on what it is they've learned. I think it's important for them to be more sort of pay attention to what it is they're getting from the class. And certainly for me, it helps me think about what are the key things they're learning, and are they actually realizing what I'm hoping they'll realize through this process of connecting the chemistry to safe drinking water. And so I'm just going to end this talk here with a few statements that the students over the years have submitted, where at least for me, I'm trying to see, are they making the connections across scales? So in these two quotes here, you can begin to see that students are recognizing the importance of the molecular nature of water and its implications for the properties of water that life relies on. In these two quotes here, they're sort of going the next step where they're connecting, again, the molecular nature of water to access to safe drinking water, looking at this connection between the chemistry and the social implications about the molecular nature of water. And this final quote here, it's rather long, I apologize, but it's what I thought was interesting here is for this student, it was also thinking about the importance of education, and how introducing these kinds of issues to students helps them sort of understand, sort of value what it is they're learning in the classroom, but also thinking about ways in which we need to think about introducing these important social contexts early into their education, so that as they advance in their own thinking, as they become the adults that they will be, that this way of thinking about social issues and environment issues might be also become second nature to them, because it's something they've been exposed to at a very early young age. And so to me, this was a particularly poignant way of, again, why am I trying to teach through these lenses from an educational perspective? I felt it was particularly gratifying for me personally to read this particular comment. So I realize I'm running out of time. So there are other ways in which I try to connect water. I have a lab course that I've developed that I'm happy to talk about if anybody's interested. And I'm just going to end with this slide here that I hope I've been able to show that, connecting fundamental chemistry to these larger socially relevant issues is clearly a way to engage students to see why they're learning chemistry, and to help them see the importance of a chemical perspective or a scientific perspective in these issues that they're grappling with, that they want to be part of the solution, part of the change makers, and that systems level thinking and context-based thinking and framing issues and issues of social justice and equity are really going to be critical for helping students see the relevance of science in their lives. And then I'll end now because I know I'm running out of time. Thank you for your attention. I really want to thank my students at Eugene Lang College. They've really inspired me to think about how I can teach chemistry in ways that that they can see the relevance of. And it's been a real amazing learning opportunity for me. I'm constantly learning. My colleagues at my department and at my institution, and thank you all for your attention.
Bhawani, thank you. That was awesome. And I think the comments you might see there now show it so. People are interested in your materials. Jess is going to do a little moderation with the Q&A, and we're going to extend that into the 5-minute break built in before the next session. So if you want to step away, by all means do so, but feel free to stay and join the Q&A. Thank you. Bhawani, thank you. That's excellent.
Thank you so much. I'm sorry if I went over.
No worries. We want more. I want more.
All right, thank you. That was amazing. There were definitely some questions about content, and there were some questions about the course as well. So I'm just going to start with the labs. I think Katayun shared a little bit about labs, but there was some curiosity about any lab components or what that looked like for this course.
Thank you. So for this particular class, there is no lab components, but what I do actually, I do a lot of molecular modeling simulations in the classroom. So again, to help provide another way in which students can visualize these molecular concepts, and so there are, I guess I won't call them simulated lab, the computer-based activities that we do in the classroom to provide another way for students to have a visually representing these very abstract concepts. But then, like I said, because the way we've designed our courses at our institution, I do have a separate lab class that I sort of flashed that slide at the end at, where they do look at ways in which the importance of quantification, experimental design, methodology, data quality, in measuring what safe means in a more quantitative approach.
Thank you. And then a question that I had that I would love to hear your response to is, were there particular either policies or community examples that the students really gravitated towards? I'd love to hear more about where their interest really lied in this experience.
Yeah, so the way I've done this is I've done it a few different ways of late. Like I said, in part one of that project, it's rather generic in that we're looking at the United States for them just to understand what are the policy frameworks here in the delivery of safe drinking water from source to tap. So they look into the Safe Drinking Water Act. They begin to be familiar with what contaminants are regulated in their act, at what levels. It's like I said, it rather, it happens at the end of the semester, so I'd really introducing them to the Safe Drinking Water Act. And again, for them to see, when I first pull up the website, it's like 90 plus contaminants regulated. It's an enormous list. And that itself is mind boggling, right? And so to your point then, in part one, and then again, to bring it back home to their own towns, is they end up looking at their drinking water quality of their own reports of their own town, so they can see what's happening in their own neighborhood. In part two, I've done it in a couple of different ways, but more recently, I've been wanting them to think about sort of ways to approach this challenge, which are not just so resource intensive, which is how we have tended to look at things in the United States. And so to your question, there's a range of different treatment approaches that have been developed across the globe, which are really meant for community-based. So there's no one that they particularly gravitate to, but I think what they take away from that is, again, its complexity, right? The system might look rather simple. But actually maintaining these drinking water systems by communities is actually not trivial. It requires a lot of time. It requires a lot of expertise, a lot of management. There's a treatment system called a biosand filter, for example, that to maintain it, to make sure the water that comes out is safe over time is not trivial. And so they begin to realize, my God, these communities, what all they have to do, in addition to their daily challenges, in delivering safe drinking water, right? Whereas again, I open up my tap, I drink it, I don't think about it. So it's just, again, for them to sort of pay attention to not to take these systems for granted, and to begin to pay attention to the invisible infrastructure as well as the invisible chemistry.
Thank you so much. So we'll take just a 1 minute quick break. I know there's definitely some interest if you're willing to share any of your materials, Bhawani. Thank you again for a fabulous opening plenary.
Thank you so much. I'd be happy to.
Okay,
and I would like to add that we should add to the SENCER mission to make the invisible visible. Thanks so much, Bhawani.
Thank you.